Hello there, and welcome to Sleep Science, where we explore fascinating science in a quiet, relaxing way that helps your mind unwind and drift off to sleep. Tonight, we're taking a slow, peaceful journey through the cosmos to meet some of the most extraordinary objects in existence: stars. Not just any stars, but the absolute giants among them. Stars so large, they make our sun look like a grain of sand on an endless beach. Before we begin tonight's cosmic voyage, feel free to share what time it is and where you're listening from. It's always wonderful to know where these quiet little science stories are drifting off to around the world. There's no need to follow every detail. Just let the gentle current of wonder carry you wherever it will. So settle in, close your eyes if you like, and let's take a slow, dreamy journey to meet the largest star in the universe. We begin our journey not in the stars, but right here at home with Earth. Not because our planet has anything particularly stellar about it, mind you, but because we need somewhere familiar to start. Think of Earth as our cosmic measuring stick, a comfortable reference point before we venture into realms where size becomes almost meaningless. Earth feels pretty substantial when you're walking around on it. All those mountains and oceans, continents stretching for thousands of miles. But in the grand scheme of stellar sizes, our planet is barely a speck. It's like trying to measure an ocean with a teaspoon. The teaspoon works perfectly fine for what it is, but it gives you no real sense of just how much water is out there. Imagine, if you will, that Earth is a marble sitting on your kitchen table, a nice blue marble with swirls of white clouds painted on it. Now, picture trying to build something the size of our sun using marbles like that one. You'd need over 1,300,000 of them. That's more marbles than you could count in several lifetimes, more than would fit in most buildings, enough to fill a decent-sized mountain. But here's the thing that makes the mind quietly boggle. The sun itself, massive as it sounds, is absolutely tiny compared to the giants we'll be meeting tonight. It's like comparing that marble Earth to a beach ball, then discovering there are objects out there the size of hot air balloons, circus tents, and eventually entire football stadiums floating through space. The beautiful thing about scale is how it puts everything into perspective. When you're stuck in traffic or worried about tomorrow's weather, it can be strangely comforting to remember that you're sitting on a small blue world orbiting a medium-sized star in one galaxy among billions. Not to make your problems feel small, but to remind you that you're part of something wonderfully vast and ongoing. Space has this gentle way of making everything feel both infinite and intimate at the same time. The distances are so large, they become almost poetic rather than practical. When we say a star is 1,000 light years away, that's not really a distance you can walk or drive or even truly imagine. It's more like a dream number, a way of saying very, very far, but still somehow connected to us by starlight. So, as we drift from Earth toward increasingly massive objects, remember that each step up represents not just bigger numbers, but entire new categories of existence. Each jump in scale is like opening a door to a room you never knew existed in the cosmic house. And perhaps most wonderfully of all, the atoms that make up your body right now were once inside stars much larger than our sun. You are, quite literally, made of star stuff. So in a way, we're not just observers on this journey, we're distant relatives, going to visit the family. The universe has a lovely sense of connection that way. From the smallest pebble on Earth to the largest star we'll meet tonight, it's all part of the same continuous story, the same slow dance of matter and energy that's been going on for billions of years. Before we meet the true giants of the cosmos, we should probably visit some objects that have stellar ambitions but never quite made it to the big leagues. Picture, if you will, Jupiter, the largest planet in our solar system. It's 11 times wider than Earth and 318 times more massive. If Earth is our marble from before, Jupiter is more like a bowling ball. A very large, very gassy bowling ball that spins once every 10 hours and has dozens of moons dancing around it like a cosmic carnival. Now, here's something curious about Jupiter. It's made of roughly the same stuff as our Sun, mostly hydrogen with a dash of helium and a sprinkling of other elements. In many ways, it's like a star that just didn't have the ambition to get big enough to actually become one. It's star adjacent, you might say, star curious. Scientists call objects like Jupiter sub-brown dwarfs, which sounds like a fantasy character who didn't quite make it into the main story. They're too big to be regular planets, but too small to start the nuclear fusion that defines a real star. They exist in that comfortable middle ground, content to reflect sunlight rather than make their own. But Jupiter isn't alone in this category. Throughout the galaxy, there are countless gas giants drifting through space, some much larger than Jupiter, some smaller. Many of them don't even orbit stars. They're just wandering through the darkness, cool and solitary. These rogue planets, or orphan worlds, might sound lonely, but there's something peaceful about them, floating freely through space at their own pace. The interesting thing about these almost stars is that if you added more mass to Jupiter, it wouldn't actually get much bigger, it would just get denser. Imagine trying to stuff more air into a balloon, but instead of expanding, the balloon just gets heavier and more tightly packed. That's what happens to gas giants as they accumulate more material. This process creates some truly odd objects. Picture a ball of gas with the mass of many Jupiters, but still roughly the same size as our solar system's giant. It would be incredibly dense, with a core under enormous pressure, but not quite enough to ignite the fusion reactions that power stars. It's like having all the ingredients for a campfire, but not quite enough heat to get it started. These massive gas balls do generate some heat, though. The pressure in their cores can trigger very slow nuclear reactions, making them glow dimly in infrared light. If you could see infrared with your eyes, they'd look like faint, warm embers scattered throughout space. Not bright enough to light up planets, but warm enough to remind you that they're trying. There's something endearing about these failed stars. They're like cosmic underachievers, perfectly content to exist without the drama and intensity of true stellar life. While real stars burn bright and fast, these gentle giants just glow quietly in the dark, warming themselves on the slow burn of nuclear reactions that barely qualify as fusion. They remind us that the universe has room for all kinds of objects, not just the show-offs. Sometimes, the most peaceful existence is found in the middle ground, being neither one thing nor another, but something uniquely in between. Between the peaceful gas giants and the brilliant stars lies a realm of cosmic disappointment, populated by objects that tried to become stars but just couldn't quite manage it. Meet the brown dwarfs, the universe's most famous underachievers. They have such a wonderfully melancholy name, don't they? They're not actually brown, by the way. That's just what astronomers call them because they're not bright enough to appear any particular color to our eyes. In reality, they probably glow with a dull red light, like the embers of a fire that's almost gone out. Brown dwarfs have between 13 and 80 times the mass of Jupiter. That might sound like a lot, but in the stellar world, it's barely enough to get noticed. Imagine trying to start a bonfire with just a handful of twigs. You might get a few small flames, maybe some smoke, but you're never going to get that roaring fire you were hoping for. These objects occupy a peculiar position in the cosmic family tree. Too massive to be planets, too small to be proper stars, they exist in a category all their own. They're like the middle children of space, often overlooked in favor of their more dramatic siblings. But here's what makes brown dwarfs particularly fascinating. They do achieve some nuclear fusion, just not the vigorous hydrogen burning that defines real stars. Deep in their cores, under enormous pressure, they can fuse heavier forms of hydrogen called deuterium. It's a much slower, more subdued process than stellar fusion, like the difference between a crackling campfire and a barely glowing piece of charcoal. This minimal fusion gives brown dwarfs a gentle warmth. They're not cold like planets, but they're not blazingly hot like stars. If you could somehow stand on the surface of one, assuming you had appropriate protection from the crushing atmosphere, you might find it pleasantly warm, like standing in a hot, humid greenhouse in the middle of winter. The life of a brown dwarf is remarkably peaceful. Unlike stars, which burn through their fuel in cosmic haste, brown dwarfs can glow dimly for trillions of years. They're the tortoises of the cosmic race, content to burn slowly and steadily while their stellar cousins flame out in mere millions or billions of years. What's particularly charming about brown dwarfs is how they challenge our need to categorize everything. They refuse to fit neatly into the boxes we've created. Are they planets? Not really. Are they stars? Not quite. They exist in that comfortable gray area, reminding us that the universe is far more nuanced and interesting than our simple classifications might suggest. Many brown dwarfs wander through space alone, too dim to be easily spotted, but numerous enough that there might be billions of them in our galaxy. Others orbit real stars at great distances, like shy relatives who show up to family gatherings but stand quietly in the corner. Some brown dwarfs even have their own tiny planets orbiting them. Imagine that, a failed star with its own little planetary system, a cosmic reminder that even the universe's underachievers can still play host to smaller worlds. There's something deeply relatable about brown dwarfs. They remind us that not everything in the universe needs to be spectacular or record-breaking to have value. Sometimes the most interesting objects are the ones that exist between categories, the ones that don't quite fit the mold but persist anyway, glowing quietly in their own unique way. In a cosmos filled with brilliant stars and dramatic explosions, brown dwarfs offer us something different. The beauty of gentle persistence, the quiet dignity of being exactly what you are, even if what you are doesn't have a perfect name. Now we arrive at the threshold where objects stop being wannabe stars and become the real thing. The moment when this transformation happens is quite dramatic, actually, even though it might take thousands or even millions of years to unfold. Picture a massive ball of gas slowly contracting under its own gravity, getting hotter and denser at the center with each passing millennium. The temperature rises gradually, like water heating on a stove, until suddenly something magical occurs. Deep in the core, hydrogen nuclei start moving fast enough and pressing close enough together that they overcome their natural repulsion and fuse into helium. When this happens, tremendous amounts of energy are released, enough to push back against the crushing weight of gravity. The star ignites, like a cosmic furnace finally reaching the temperature needed to sustain itself. This is the beginning of what astronomers call the main sequence, the long, stable phase of a star's life when it burns hydrogen in its core. It's the stellar equivalent of adulthood, a time of steady productivity and reliable energy output. Most stars spend the majority of their lives in this phase, contentedly converting hydrogen to helium and light. But here's where things get counterintuitive. The more massive a main sequence star is, the shorter and more intense its life becomes. It's like the cosmic equivalent of living fast and dying young. A massive star burns its fuel with such intensity that it can exhaust its core hydrogen in just a few million years, while smaller stars can sip their fuel so slowly they'll shine for trillions of years. This relationship between mass and lifetime creates one of the beautiful ironies of stellar life. The biggest, brightest, most impressive stars are also the most short-lived. They're like brilliant candles that burn twice as bright but last half as long, while the small, dim stars are like steady nightlights that will outlast everything else in the galaxy. The fusion process itself is quietly extraordinary. 4 hydrogen nuclei somehow manage to stick together through a complex series of steps, transforming into one helium nucleus. The process releases energy in the form of light and heat, but it also creates something else: time. The balance between the outward pressure from fusion and the inward pull of gravity gives stars their stability, their predictable life cycles, their gentle, steady burning. Inside a star like our Sun, it takes hundreds of thousands of years for light created in the core to work its way to the surface. The photons bounce around like pinballs, absorbed and re-emitted countless times as they slowly drift outward through the dense stellar interior. By the time that light reaches your eyes, it's been on quite the journey. Main sequence stars come in a delightful variety of sizes, colors, and temperatures. The smallest ones glow with a cool red light and are barely larger than Jupiter. The largest ones shine brilliant blue-white and contain dozens of times more mass than our Sun. Each one has its own personality, its own way of balancing the competing forces that define stellar life. What's particularly wonderful about main sequence stars is their reliability. They settle into a rhythm and stick with it for millions, billions, or even trillions of years. They're the steady heartbeat of the galaxy, the reliable sources of light and warmth that make planetary systems possible. Our Sun is a perfect example of this stellar stability. For 4.5 billion years, it has maintained roughly the same brightness and temperature, creating the steady conditions that allowed life on Earth to develop and flourish. Every sunrise is a reminder of this cosmic consistency, this gentle persistence of nuclear fusion happening 93 million miles away. At the bottom of the stellar size ladder, just barely massive enough to call themselves proper stars, we find the red dwarfs. These modest little stars are only about 8% the mass of our Sun, making them roughly 10 times more massive than Jupiter, but still surprisingly small as stars go. If our Sun were a basketball, a red dwarf would be about the size of a tennis ball. They're the cosmic equivalent of efficiency apartments, small, economical, and built to last. Red dwarfs burn their fuel with the same careful conservation as someone living on a tight budget. They fuse hydrogen so slowly and gently that they can keep shining for 10 trillion years. That's 1,000 times longer than the current age of the universe. If red dwarfs were people, they'd be the ones who save every penny, turn off lights when leaving the room, and somehow make a single bag of groceries last for weeks. The light from a red dwarf is dim and ruddy, like the glow from dying coals in a fireplace. They're so faint that despite being the most common type of star in the galaxy, you can't see a single one with your naked eye. The nearest red dwarf to Earth, Barnard's star, is only about 6 light-years away, practically next door in cosmic terms, but it's completely invisible without a telescope. There's something almost cozy about red dwarfs. They seem like the kind of stars that would have small, close-knit planetary families where any worlds orbiting nearby would be tidally locked, with one side always facing the star like a planetary face perpetually warmed by gentle stellar light. The day side might be pleasantly warm while the night side stays cool, creating interesting weather patterns and temperature gradients. Because they burn so slowly, red dwarfs don't go through the dramatic expansion phases that larger stars experience. When they eventually run out of fuel billions of years from now, they don't swell up into giants or explode as supernovas. They simply fade away, cooling slowly from red to brown to black, becoming stellar embers drifting through space. This makes red dwarfs remarkably stable companions for any planets that might orbit them. While massive stars live fast and die young, often sterilizing their neighborhoods with intense radiation or explosive deaths, red dwarfs provide a steady, reliable source of warmth for geological ages. If life needs billions of years to develop complexity, red dwarfs offer the ultimate in long-term stability. In our galaxy, red dwarfs vastly outnumber all other types of stars combined. They're the quiet majority, the unassuming background stars that don't draw much attention but form the backbone of the galactic community. While we often focus on the dramatic blue giants and explosive supernovas, red dwarfs are busy being dependable, shining quietly in their corners of space. There's a certain beauty in their modesty. Red dwarfs don't try to be spectacular. They don't compete for attention or burn bright enough to outshine their neighbors. They simply exist, doing their job of converting hydrogen to helium with steady, unflashy efficiency. Some scientists speculate that red dwarfs might be the best places to look for long-lived civilizations. Their incredible longevity means that any life forms that develop in their vicinity would have vast amounts of time to evolve and grow complex. While our Sun will eventually expand and engulf Earth in about 5 billion years, planets around red dwarfs could remain habitable for thousands of times longer. These little stars remind us that sometimes the most impressive thing is not drama or intensity, but simple persistence. In a universe full of spectacular events and cosmic fireworks, red dwarfs offer something different. The quiet beauty of endurance, the gentle comfort of knowing that some things are built to last. Now let's visit something familiar, stars like our own Sun. Our Sun is what astronomers call a yellow dwarf, though it's actually more of a yellowish white if you could see it from space without Earth's atmosphere filtering the light. It's a wonderfully average star in almost every way, sitting comfortably in the middle of the stellar size range like someone who orders the medium-size everything and finds it suits them perfectly. To say the Sun dominates our solar system understates things considerably. It contains 99.86% of all the mass in the solar system. All the planets, moons, asteroids, comets, and cosmic dust combined make up barely more than 1/10% of what's here. If the solar system were a family, the Sun would be the parent who pays all the bills, owns the house, and makes all the important decisions, while the planets would be the children arguing over who gets to use the car. The Sun burns about 4 million tons of itself every second, converting that mass into pure energy through Einstein's famous equation E equals mc squared. That might sound alarming, like our star is rapidly wasting away, but don't worry. At this rate, it would take about 5 billion years for the Sun to lose just 1% of its mass. It's like having a bank account so large that even spending thousands of dollars every day, you'd barely notice the difference for millions of lifetimes. This steady burning gives our Sun a surface temperature of about 5,500 degrees Celsius, hot enough to vaporize any known material instantly, but actually quite moderate for a star. The light it produces is that perfect blend of colors we call white light, containing all the wavelengths our eyes can see, plus ultraviolet and infrared that we can't. The Sun's energy doesn't just provide heat and light, it drives virtually every process on Earth. The wind is powered by solar heating. Rain falls because the Sun evaporates ocean water. Plants grow by capturing sunlight and converting it to chemical energy. In a very real sense, almost all the energy we use on Earth is solar energy, just stored and converted into different forms. Sun-like stars have lifespans of about 10 billion years, long enough for complex planetary systems to develop and evolve. Our Sun is currently middle-aged at about 4.6 billion years old, settled comfortably into its routine of steady hydrogen burning. It has another 5 billion years or so of stable burning ahead before it begins to change in ways that will make Earth less hospitable. What makes sun-like stars particularly special is their stability. They don't flare up with dangerous radiation bursts like smaller stars sometimes do. They don't burn through their fuel so quickly that planets never have time to develop thick atmospheres or complex chemistry. They provide just the right amount of energy at just the right consistency to allow delicate processes like life to take hold and flourish. The Sun is also perfectly positioned in our galaxy, sitting in what astronomers call the galactic habitable zone, far enough from the galactic center to avoid dangerous radiation and gravitational disruption, but close enough to have access to the heavy elements created by earlier generations of stars. It's like living in the suburbs of the galaxy, peaceful, stable, with good schools and parks nearby. Stars like our Sun are common enough that there are probably billions of them in our galaxy, but not so common that they're unremarkable. They represent a kind of stellar sweet spot, massive enough to burn steadily for billions of years, but not so massive that they race through their life cycle and explode before planets can develop interesting chemistry. In the gentle light of stars like our Sun, worlds can warm slowly, develop atmospheres, accumulate water, and perhaps, if conditions are just right, nurture the slow, patient processes that eventually lead to life looking up at the stars and wondering about its place in the cosmos. As we climb higher up the stellar mass ladder, we encounter the cosmic equivalent of race cars, brilliant, powerful, and destined to burn out quickly. Massive blue stars are the superstars of the galaxy, literally and figuratively. Take Sirius, the brightest star in our night sky. It's twice as massive as our Sun, but that seemingly small difference translates into extraordinary changes. Sirius shines 25 times brighter than the Sun and burns at a surface temperature of nearly 10,000 degrees Celsius, hot enough to give it that distinctive blue-white light that makes it twinkle so brilliantly in winter skies. The relationship between stellar mass and brightness is one of those cosmic facts that seems almost magical. A star just twice as massive as the Sun doesn't shine twice as bright. It shines 25 times brighter. It's like the universe has a built-in amplification system where small changes in size produce enormous changes in output. This happens because massive stars have higher core temperatures and pressures, which make fusion reactions proceed much more rapidly. But this intensity comes at a cost. While our Sun will burn steadily for about 10 billion years, Sirius will exhaust its core hydrogen in only about 200 million years. It's the stellar equivalent of living life in the fast lane. Brilliant, dramatic, and relatively brief. Even more extreme are stars like Beta Centauri, which contains two massive blue stars orbiting each other in a cosmic dance. Each of these stars has about 10 times the mass of our Sun and shines with about 10,000 times its power. Their surface temperatures reach about 28,000 degrees Celsius, so hot that most of their light is emitted in the ultraviolet range, invisible to our eyes, but deadly to any nearby planets. These massive stars live in a constant state of barely controlled explosion. The nuclear fusion in their cores is so vigorous that it creates tremendous pressure pushing outward, barely balanced by their own gravity pulling inward. They're like cosmic pressure cookers operating right at the edge of stability. The light from these stellar giants is so intense that it can affect the space around them for dozens of light years in all directions. They ionize nearby gas clouds, making them glow like neon signs scattered through space. Entire star-forming regions can be lit up by just a few massive blue stars, creating some of the most beautiful nebulae in the galaxy. But perhaps most remarkably, these stars burn so hot and fast that entire generations of them can live and die in the time it takes our Sun to complete just one orbit around the galaxy. While the Sun plods along its 230 million-year galactic orbit, massive blue stars are born, live their intense lives, and explode as supernovas, sometimes within just a few million years. This rapid life cycle means that massive blue stars are relatively rare. They're like exotic sports cars. Impressive when you see them, but not the kind of thing you encounter every day. Most of the massive blue stars that existed when our galaxy was young have long since exploded, seeding space with the heavy elements that make planets and people possible. The existence of massive blue stars also tells us something profound about star formation. These giants can only form in special circumstances, in dense stellar nurseries, where vast amounts of material can come together quickly enough to build such massive objects. They're products of cosmic abundance, requiring the right conditions and plenty of raw material. Despite their brief lives, massive blue stars play crucial roles in galactic evolution. Their intense stellar winds blow away nearby gas and dust. Their ultraviolet light regulates star formation in their neighborhoods, and when they finally explode, they scatter heavy elements throughout space and can trigger new waves of star formation with their shock waves. They remind us that in the universe, brightness and longevity don't necessarily go together. Sometimes the most spectacular things are also the most fleeting, burning bright and beautiful, precisely because they can't sustain that intensity forever. Now, we come to one of the most fascinating puzzles in stellar astronomy. Why don't we find stars that are arbitrarily massive? You might think that if you just keep adding more and more material to a forming star, you could make it bigger and bigger indefinitely. After all, gravity is always trying to pull more matter inward. So, what's to stop a star from growing to enormous proportions? The answer, as it turns out, is the star itself. Meet Roan 136 Awone, currently the most massive star we know of. It weighs in at about 315 times the mass of our Sun and shines nearly 9 million times brighter. To put this in perspective, if our Sun were a modest campfire, Roan 136 Awone would be like a blast furnace that could melt steel from several miles away. But here's the thing. Despite its tremendous mass and power, Roan 136 Awone is barely 50 times the diameter of the Sun. You might expect something so much more massive to be correspondingly larger, but massive stars don't work that way. They pack their extra mass into a relatively small volume, creating extreme conditions that lead to their own limitation. Roan 136 Awone is so energetic that it's literally blowing itself apart. Every second, it loses about 16 billion tons of material through what astronomers call stellar wind. That's roughly equivalent to the mass of a large mountain being blown away every second. The star is so hot and bright that its own light pressure pushes its outer layers into space, like trying to hold onto a fistful of sand while someone aims a fire hose at your hand. This creates a natural limit to how massive stars can become. When a supermassive star forms, it burns so hot and bright that it blows away any additional material that might otherwise fall onto it and make it even more massive. It's like a cosmic thermostat that prevents stars from growing beyond a certain size. The theoretical upper limit for stellar mass is around 350 times the mass of our Sun, and even reaching that limit requires very special circumstances. Most stars like Roan 136 Awone probably formed through the merger of several smaller, massive stars in dense stellar nurseries, where gravitational interactions can push smaller stars together until they combine into supermassive objects. These stellar monsters live incredibly brief lives, even by the standards of massive stars. While a typical blue giant might burn for 10 or 20 million years, stars like Roan 136 Aun exhaust their core fuel in just a few million years. They're like cosmic mayflies, spectacular but ephemeral. The rarity of such massive stars also tells us something important about the universe. In the early cosmos, when the first generation of stars formed, conditions might have been different enough to allow for even more massive stars. These hypothetical population 3 stars might have been hundreds of times more massive than anything we see today, living brief, brilliant lives before exploding and seeding the universe with the first heavy elements. But in today's universe, with its mix of hydrogen, helium, and heavier elements, the formation of extremely massive stars requires special conditions. Dense star clusters, unusual amounts of available material, and just the right timing all need to come together to create these stellar giants. There's something almost poetic about the fact that the most massive stars are limited by their own success. They burn so brightly that they prevent themselves from growing even larger, like cosmic examples of the principle that sometimes more isn't necessarily better. This mass limit also affects the ultimate fate of these stars. Stars above a certain mass threshold are destined to end their lives in the most violent explosions in the universe. Pair instability supernovas that can briefly outshine entire galaxies. They literally destroy themselves so thoroughly that nothing remains, not even a black hole. In the end, even the universe has its limits, and the maximum mass of stars represents one of those fundamental boundaries that shape the cosmic landscape and determine what kinds of objects can exist in our universe. Here's where our story takes a fascinating turn. Sometimes, to become truly gigantic, a star must first begin to die. When main sequence stars start to exhaust the hydrogen fuel in their cores, something counterintuitive happens. Instead of shrinking and dimming, they actually begin to expand, sometimes growing to hundreds of times their original size. It's like watching a candle that's almost burned out suddenly flare up into a bonfire. The process begins when a star has spent millions, billions, or even trillions of years steadily converting hydrogen to helium in its core. Eventually, the hydrogen fuel runs low, and the fusion reactions that have been keeping the star inflated begin to weaken. With less energy pushing outward, gravity starts to win the ancient battle, and the core begins to contract. But here's where stellar physics gets delightfully weird. As the core shrinks, it heats up, and this increased temperature causes hydrogen burning to begin in a shell around the now inactive core. This shell burning is more vigorous than the original core fusion, producing more energy than the star has ever generated before. All that extra energy has to go somewhere, and where it goes is outward, pushing the star's outer layers into a vast, tenuous envelope. Take Gakrux, for example. This star has only about 30% more mass than our Sun, but it has swollen to about 84 times the Sun's radius. If you could somehow replace our Sun with Gakrux, its surface would extend beyond the orbit of Mercury. The star has become a cosmic balloon, with most of its volume occupied by extremely thin, hot gas. Our own Sun is destined for this fate. In about 5 billion years, as it begins to run out of core hydrogen, it will start to expand into a red giant. At its maximum size, it will grow to about 250 times its current radius, reaching out to engulf the orbits of Mercury and Venus, and making Earth a very uncomfortable place indeed. The outer layers of a red giant are so tenuous that they're almost like a hot, glowing atmosphere extending far into space. The density is so low that it's essentially a vacuum by Earth standards, but it's a very hot vacuum, glowing with the warmth generated by the active shell burning deeper inside. This expansion phase doesn't last very long in stellar terms, perhaps a few million years for a sun-like star. It's a brief, dramatic chapter in a star's life, like the finale of a fireworks display. The star burns brighter than ever before, but it's also using up its remaining fuel at an accelerated rate. During this red giant phase, stars become some of the most luminous objects in their local neighborhoods. They can outshine dozens of main sequence stars combined, becoming visible from tremendous distances. Many of the brightest stars in our night sky are actually red giants, their swollen sizes making them apparent even from hundreds of light years away. The red giant phase is also when stars begin to lose significant amounts of mass. The outer layers are so loosely bound that stellar winds can carry away substantial portions of the star's material, creating beautiful, glowing shells of gas called planetary nebulae. It's as if the star is gently breathing out its outer layers, returning processed material to space. This mass loss is actually crucial for the formation of the largest stars we know. Some red giants lose so much material that they create spectacular shells and rings of glowing gas around themselves, visible for thousands of years after they've shed their outer layers. For stars more massive than our Sun, the red giant phase is just the beginning of an even more dramatic expansion story. They can grow through multiple expansion phases, each one making them larger and more luminous than the last, until they become the true monsters we'll meet next. Welcome to the realm of the hypergiants, where stars become so large that they challenge our ability to comprehend size itself. Hypergiants represent the most extreme possible outcome of stellar evolution, the result of the most massive stars entering their final, spectacular phases of life. These are objects that have pushed the boundaries of what it means to be a star, growing so large that they're essentially blowing themselves apart while still trying to burn fuel in their cores. The defining characteristic of hypergiants isn't just their size, though that's certainly impressive, but their instability. These stars exist in a constant state of barely controlled chaos, their outer layers so loosely bound that they're constantly losing mass to space through powerful stellar winds. It's like trying to hold together a cloud made of fire, gas, and pure energy. Hypergiants come in different varieties, classified by their color and temperature, but they all share certain characteristics. They're all extremely luminous, often shining with the power of hundreds of thousands of suns. They're all unstable, varying in brightness over time as they pulse and shed material. And they're all relatively short-lived, burning through their final fuel reserves in just a few million years. The sheer scale of these objects defies easy comparison. When we talk about stars dozens of times larger than our Sun, we quickly run out of familiar analogies. If our Sun were the size of a basketball, some hypergiants would be as large as sports stadiums. But even that comparison fails to capture the reality, because hypergiants aren't solid objects like stadiums, they're tenuous, glowing envelopes of superheated gas. What makes hypergiants possible is a delicate balance between competing forces. Their enormous luminosity creates radiation pressure that tries to blow the star apart. Their massive gravity tries to hold everything together. Their internal fusion reactions generate the energy that powers their luminosity, and stellar winds carry away material that would otherwise make them even larger. All these forces dance together in a complex, ever-changing equilibrium that can shift over relatively short timescales. Many hypergiants are variable stars, meaning their brightness changes over time. Some of these variations are regular and predictable, caused by the star pulsing like a gigantic heart. Others are irregular and chaotic, reflecting the unstable nature of these extreme objects. A hypergiant might suddenly dim by several magnitudes, then slowly brighten again as its outer layers redistribute themselves. The stellar winds from hypergiants are unlike anything produced by normal stars. They can carry away material at speeds of hundreds of kilometers per second, creating vast shells and nebulae around the star. Some hypergiants are surrounded by their own expelled material, creating complex, beautiful structures that astronomers can observe long after the material was ejected. Despite their enormous size and power, hypergiants are remarkably rare. In our entire galaxy, there might be only a few dozen of them at any given time. This rarity isn't just because they're short-lived, though that's part of it. It's also because creating a hypergiant requires very specific conditions: a very massive progenitor star, the right metallicity, and probably some luck in terms of stellar evolution. The study of hypergiants has revealed important insights about stellar physics and the limits of what stars can become. They represent the absolute upper end of stellar evolution, the largest, most luminous, most unstable objects that can still technically be called stars. Beyond hypergiants, we enter the realm of other exotic objects. Stellar explosions, black holes, and phenomena that challenge our definitions of what constitutes a single astronomical object. These stellar giants remind us that the universe contains objects of almost unimaginable scale and power, yet they exist within the same physical laws that govern everything else. They're extreme, but they're not impossible, pushing the boundaries of stellar physics while still remaining comprehensible through the same principles that explain our gentle sun. Among the hypergiants, the blue ones burn with an intensity that borders on the impossible. Blue hypergiants are what you get when you take an already massive star and push it to its absolute limits. These objects are so hot that their surface temperatures can exceed 50,000 degrees Celsius, making them shine with an intense blue-white light that contains enormous amounts of ultraviolet radiation. They're like cosmic blowtorches, so energetic that they can ionize gas clouds from dozens of light years away. One of the best-studied blue hypergiants is the Pistol Star, located about 25,000 light-years away in the constellation Sagittarius. Despite being roughly 150 times the mass of our Sun, the Pistol Star is only about 300 times its radius. This might sound large, but for such a massive object, it's actually quite compact. All that mass compressed into a relatively small volume, creating extreme conditions at every level. The Pistol Star shines with about 10 million times the luminosity of our Sun, making it one of the most powerful single objects in our galaxy. If you could somehow replace our Sun with the Pistol Star, the increased energy would vaporize Earth almost instantly. The intense radiation would strip away planetary atmospheres throughout the solar system and ionize any remaining material into glowing plasma. What makes blue hypergiants particularly fascinating is their instability. The Pistol Star, for example, has been observed to vary significantly in brightness over just a few decades. It's surrounded by the Pistol Nebula, a shell of glowing gas that the star expelled in a massive eruption sometime in the past few thousand years. This nebula contains about 10 times the mass of our Sun, material that was once part of the star's outer layers, but was blown away by the star's own intense radiation and stellar winds. The stellar winds from blue hypergiants are extraordinary phenomena in their own right. The Pistol Star loses material at a rate millions of times greater than our Sun, creating winds that race away from the star at speeds of several thousand kilometers per second. These winds are so energetic that they heat up nearby space to millions of degrees, creating X-ray emissions that can be detected by space telescopes. Blue hypergiants exist in a constant state of near explosion. The radiation pressure from their intense fusion reactions pushes so hard against their outer layers that they're always on the verge of blowing themselves apart completely. Only their tremendous gravitational pull keeps them from immediately dispersing into space, and even then, they're constantly losing the battle, shedding material through their powerful stellar winds. The lifetime of a blue hypergiant is measured in mere millions of years, incredibly brief even by the standards of massive stars. They burn through their nuclear fuel so rapidly that they can exhaust their cores in less time than it takes for complex life to evolve on nearby planets. They're cosmic sprinters, running at full speed for their entire brief existence. Because of their extreme luminosity, blue hypergiants can be seen from tremendous distances. Even though they're rare, their intense brightness makes them visible across large portions of the galaxy. Astronomers can study blue hypergiants in other galaxies millions of light-years away, using them as probes of stellar evolution and star formation in distant cosmic environments. The end fate of blue hypergiants is still somewhat uncertain, but it's likely to be spectacular. They may explode as luminous blue variables, ejecting their outer layers in violent eruptions. They might collapse directly into black holes, or they could undergo pair instability supernovas, explosions so powerful that they completely destroy the star and leave nothing behind. These stellar powerhouses represent the absolute peak of stellar energy output, the most luminous single objects that stellar evolution can produce. They exist at the very limits of what's physically possible for a star, blazing with an intensity that pushes against the fundamental forces that govern stellar structure. Between the blazing blue hypergiants and the enormous red ones lies a small group of stars that occupy one of the most exclusive clubs in the galaxy. Yellow hypergiants are so rare that astronomers have identified only about a dozen of them in our entire galaxy. They're thought to represent a brief, unstable phase that the most massive stars pass through as they evolve from their blue giant phase toward becoming red hypergiants. It's like catching a star in the middle of changing clothes, an awkward intermediate stage that doesn't last very long. The most famous and well-studied yellow hypergiant is Rho Cassiopeiae, a star so bright that despite being thousands of light years from Earth, you can still see it with the naked eye on a clear night. At about 40 times the mass of our Sun, Rho Cassiopeiae has expanded to roughly 400 times the Sun's radius, making it large enough that if it were placed at the center of our solar system, its surface would extend well beyond the orbit of Mars. What makes Rho Cassiopeiae particularly fascinating is its tendency to undergo dramatic eruptions. In the year 2000, astronomers watched as the star dimmed significantly, dropping to about 6% of its normal brightness over the course of several months. This wasn't a gradual dimming, but a sudden, dramatic event caused by the star ejecting a massive shell of material from its outer layers. During this eruption, Rho Cassiopeiae ejected about 1.5 times the mass of our Sun in a matter of months. Imagine our entire Sun being blown away like dust in a cosmic sneeze, and you begin to get a sense of the violence involved. The ejected material formed a shell around the star that continued to expand and glow for years afterward. Yellow hypergiants are thought to be in a particularly unstable phase of stellar evolution. They're massive enough to be extremely luminous, but they're also cool enough that their outer atmospheres are prone to dramatic instabilities. The combination of high luminosity and relatively cool surface temperature creates conditions where the star's outer layers can become unstable and be ejected in violent eruptions. The color of yellow hypergiants comes from their surface temperature, which is typically between 4,000 and 6,000 degrees Celsius. This is actually cooler than our Sun's surface, but because these stars are so much larger, they emit far more total energy. It's like comparing a small, hot blowtorch to a large, warm campfire. The campfire gives off more total heat, even though the blowtorch is hotter at any given point. The rarity of yellow hypergiants suggests that this phase of stellar evolution is very brief, perhaps lasting only a few 100,000 years. In stellar terms, that's barely a blink of an eye. Most massive stars probably pass through this phase so quickly that we're unlikely to catch many of them in the act. This brevity also makes yellow hypergiants particularly valuable for understanding stellar evolution. They represent a specific moment in the life of very massive stars, a transition period that can tell us about how these objects change over time. By studying the few yellow hypergiants we can observe, astronomers can piece together the evolutionary paths that lead from massive blue stars to enormous red hypergiants. Some yellow hypergiants show signs of being surrounded by complex structures of ejected material, the remnants of previous eruptions and mass loss episodes. These structures can provide clues about the star's history and the violent processes that govern the final phases of massive star evolution. The yellow hypergiant phase might also be associated with the formation of some of the most spectacular supernovas in the universe. When stars this massive finally exhaust their fuel, their collapse and subsequent explosion can create events visible from billions of light years away. Despite their rarity, yellow hypergiants remind us that stellar evolution is not a smooth, predictable process, but rather a series of sometimes dramatic transitions. They represent moments of cosmic change, brief interludes in the lives of the most massive stars as they transform from one type of object into another. Now we arrive at the true giants of the stellar world, objects so large that they challenge our ability to conceive of size itself. Red hypergiants are the largest individual objects in the known universe. These are stars that have grown so enormous that their surfaces would engulf the orbits of entire planetary systems. They represent the absolute upper limit of how large a single star can become while still maintaining some semblance of structural integrity. The physics of red hypergiants is both fascinating and strange. These stars have surface temperatures of only about 3,000 to 4,000 degrees Celsius, cooler than our Sun, but their sheer size means they emit hundreds of thousands of times more energy. It's like comparing a small, hot light bulb to a massive, warm fireplace. The fireplace gives off far more total heat, even though any particular spot on it might be cooler than the light bulb. One of the most remarkable things about red hypergiants is how tenuous their outer layers are. The material at their surfaces has a density lower than the best vacuum we can create on Earth. These stars are essentially enormous balls of extremely thin, hot gas, held together by gravity but constantly losing material to space through stellar winds. The largest red hypergiants can have radii more than 2,000 times that of our Sun. To put this in perspective, if you could travel at the speed of light, it would take you about 8 hours to circle around the largest of these stars. The fastest jet aircraft on Earth would take over 1,000 years to complete the same journey. If you placed one of the largest red hypergiants at the center of our solar system, its surface would extend beyond the orbit of Saturn. Jupiter, our solar system's largest planet, would be swimming around inside the star's atmosphere, along with all of its moons. The outer planets would still be orbiting outside the star, but they would be bathed in the intense heat and light from the star's surface. Red hypergiants achieve their enormous size through a combination of extreme mass loss and nuclear burning in shells around their cores. As these massive stars age, they develop complex internal structures with multiple layers of fusion reactions. Helium burning in one shell, carbon burning in another, oxygen burning deeper inside. Each of these burning shells generates energy that helps push the outer layers farther and farther from the core. But this enormous size comes at a cost. Red hypergiants are extremely unstable objects, prone to dramatic variations in brightness and violent eruptions that can eject entire solar masses of material in single events. They exist in a delicate balance between the outward pressure from their internal energy sources and the inward pull of gravity, a balance that can shift dramatically over relatively short time periods. Many red hypergiants are surrounded by shells and nebulae of material they've ejected over their lifetimes. These structures can extend for light years around the star, creating some of the most spectacular sights in the galaxy. The material in these shells is often enriched with heavy elements created inside the star, providing the raw materials for future generations of stars and planets. The lifetimes of red hypergiants are measured in hundreds of thousands to millions of years, incredibly brief for such massive objects. They burn through their remaining nuclear fuel so rapidly that they cannot maintain their enormous size for very long. Eventually, they either collapse into black holes, explode as supernovas, or undergo some other dramatic transformation. These stellar monsters represent the absolute limits of what single objects can achieve in our universe. They are the largest, most luminous, most spectacular individual things that exist, pushing against the fundamental physical constraints that govern matter, energy, and gravity on cosmic scales. In the catalogue of cosmic giants, one star currently holds the title of largest known object in the universe. Stevenson 2-18, with its rather prosaic designation, is anything but ordinary. Located about 20,000 light-years away in the constellation Scutum, this red hypergiant is so large that it stretches the boundaries of what we consider possible for a single star. Current estimates suggest that Stevenson 2-18 has a radius about 2,150 times that of our Sun. To help your mind grasp this scale, imagine that if our Sun were the size of a marble, Stevenson 2-18 would be larger than a hot air balloon. If you placed it at the center of our solar system, its surface would extend beyond the orbit of Saturn, potentially reaching as far as Uranus. The numbers become almost abstract at this scale. If you could somehow travel around the equator of this star at the speed of light, the journey would take about 9 hours. A commercial jet aircraft, flying at its typical cruising speed, would need more than 1,000 years to complete the same trip, assuming it could somehow survive the journey through the star's tenuous but superheated outer atmosphere. What makes Stevenson 2-18 even more remarkable is how much mass it has lost over its lifetime. Astronomers estimate that when this star was on the main sequence, burning hydrogen in its core, it probably contained between 25 and 40 times the mass of our Sun. Today, after millions of years of stellar winds and mass ejection episodes, it likely contains only 12 to 15 solar masses. This means that more than half the star's original mass has been blown away into space, creating vast shells and structures around the star. These expelled layers are enriched with heavy elements created in the star's interior through nuclear fusion, providing the raw materials from which future generations of stars and planets will form. The surface temperature of Stevenson 2-18 is only about 3,200 degrees Celsius, significantly cooler than our Sun's surface temperature of about 5,500 degrees. But because of its enormous size, it radiates energy at a rate nearly 500,000 times greater than our Sun. If you could somehow replace our Sun with Stevenson 2-18, Earth would be vaporized almost instantly by the intense heat. What's particularly fascinating about this star is its instability. Red hypergiants like Stevenson 2-18 are known to vary significantly in brightness over time, sometimes dimming by several magnitudes before slowly brightening again. These variations are caused by changes in the star's outer atmosphere, as material is heated, expelled, and redistributed in complex patterns. The star is also surrounded by a complex environment of dust and gas, the remnants of material it has ejected over its lifetime. This circumstellar material creates interesting optical effects, sometimes making the star appear dimmer than it actually is, and making precise measurements of its size and luminosity challenging for astronomers. Stevenson 2-18 represents the current known limit of stellar gigantism, but it's important to remember that our measurements of such extreme objects come with significant uncertainties. The star is so far away and surrounded by so much material that determining its exact size requires careful analysis of infrared observations and sophisticated modeling techniques. It's also worth noting that the title of largest known star may not belong to Stevenson 2-18 forever. As our instruments improve and we survey more of the galaxy, we may discover even larger objects. There could be red hypergiants out there that make Stevenson 2-18 look modest by comparison. But for now, this distant star holds the record as the largest single object we know of in the universe, a cosmic giant that pushes against the fundamental limits of what stellar evolution can achieve. As we reach the end of our journey through the realm of stellar giants, it's worth reflecting on the beautiful cyclical nature of cosmic evolution. Every star, from the smallest red dwarf to the largest red hypergiant, is part of an ongoing story that began billions of years ago and will continue for billions of years into the future. The elements that make up these stellar giants were created inside previous generations of stars, and when current stars die, they will return those elements plus new ones to space, where they will eventually become part of future stars. This cosmic recycling program is one of the most elegant processes in the universe. The carbon in your body was forged in the core of a dying star. The oxygen you breathe was created when a massive star exploded as a supernova. The iron in your blood was synthesized in the final moments before a stellar core collapse. You are quite literally made of processed starlight, atoms that have been through multiple cycles of stellar birth, life, and death. The largest stars play a particularly important role in this cosmic cycle. When red hypergiants finally exhaust their fuel, they don't simply fade away like smaller stars. Instead, they often explode as supernovas, events so violent that they can briefly outshine entire galaxies. These explosions scatter the heavy elements created inside the star throughout the surrounding space, seeding future star-forming regions with the ingredients needed to create rocky planets and complex chemistry. Some of the most massive hypergiants might end their lives in even more spectacular fashion in events called pair instability supernovas. These are explosions so powerful that they completely destroy the star, leaving behind no remnant black hole or neutron star, just a rapidly expanding shell of hot gas enriched with heavy elements. The shock waves from these stellar explosions can also trigger new rounds of star formation, compressing nearby gas clouds until they begin to collapse under their own gravity. In this way, the death of old stars leads directly to the birth of new ones, a continuous cycle of cosmic renewal that has been going on for most of the universe's history. Even the most massive stars we've discussed tonight are part of this cycle. Stevenson 2-18, despite its current enormous size, will eventually exhaust its remaining fuel. When that happens, its core will collapse, potentially forming a black hole, while its outer layers are expelled into space in a final, dramatic explosion. The material expelled from dying hypergiants is particularly valuable for cosmic evolution because it contains large quantities of elements heavier than hydrogen and helium. These heavy elements are crucial for the formation of rocky planets, complex molecules, and ultimately, life as we know it. In stellar astronomy, there's a beautiful concept called chemical evolution, which describes how the overall composition of the galaxy changes over time as successive generations of stars live and die. Early in the universe's history, there were only hydrogen and helium available for star formation. But as the first massive stars lived and died, they began to enrich space with carbon, oxygen, nitrogen, iron, and dozens of other elements. Today's star-forming regions contain a rich mixture of elements, allowing for the formation of diverse planetary systems and complex chemistry. The largest stars of today will add their own contributions to this ongoing enrichment process, ensuring that future generations of stars will have access to an even richer palette of elements to work with. This perspective helps put the impressive scales we've discussed into a broader context. These stellar giants aren't just impressive objects in their own right. They're active participants in the ongoing evolution of the galaxy and the universe as a whole. Picture a star so massive that it's literally blowing itself apart, one atom at a time. The stellar winds from hypergiants represent one of the most remarkable phenomena in astrophysics, a process where stars essentially evaporate into space through the sheer intensity of their own energy output. It's like watching a cosmic ice cube melt, except instead of water dripping away, we're seeing entire solar masses of material streaming into the void. To understand how this works, imagine standing next to a campfire on a windy day. The heat from the fire warms the air, making it rise and creating updrafts that carry away smoke and sparks. Now scale that up by factors of millions. Instead of wood burning, you have nuclear fusion in a stellar core. Instead of warm air, you have gas heated to tens of thousands of degrees. And instead of gentle updrafts, you have radiation pressure so intense it can accelerate particles to significant fractions of the speed of light. The process begins deep inside the star, where nuclear fusion creates not just energy, but also photons, tiny packets of light and radiation. These photons start their journey from the core, but in a normal star like our Sun, they bounce around for hundreds of thousands of years before finally reaching the surface. In a hypergiant, this journey is both easier and more violent. As photons work their way outward through the star's interior, they can transfer their momentum to atoms in the star's atmosphere. This is called radiation pressure, and it works like a constant wind pushing outward from within the star itself. For most stars, gravity is strong enough to overcome this pressure and keep the atmosphere bound to the star. But in hypergiants, the radiation is so intense that it can actually overcome gravity in the outer layers. The stellar winds from these giants are truly extraordinary. A star like our Sun loses about 1/1,000,000th of its mass each year through solar wind. That's so little that the Sun could maintain this rate of mass loss for trillions of years without significantly changing. But hypergiants lose mass at rates millions of times greater. Some can lose the equivalent of our entire Sun's mass in just a few 100,000 years. These winds don't flow smoothly like water from a faucet. Instead, they're turbulent, chaotic, and highly structured. As material streams away from the star, it can form spirals, shells, and complex knots of density. Some hypergiants show evidence of episodic mass loss, where they suddenly eject large amounts of material in dramatic outbursts, creating shells that expand away from the star like cosmic ripples. The speed of these stellar winds is equally impressive. Material can be accelerated to velocities of hundreds or even thousands of kilometers per second as it escapes from the star's gravity. At these speeds, particles ejected from a hypergiant could travel from Earth to the Moon in just a few minutes. But stellar winds aren't just about the star losing mass. They're also about enriching the space around the star with heavy elements. Deep inside massive stars, nuclear fusion creates elements far heavier than the hydrogen and helium that the star was born with. Carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements are forged in the stellar interior through successive fusion reactions. When stellar winds carry away the outer layers of the star, they're also carrying away these newly created elements, distributing them throughout the surrounding space. This process, called stellar nucleosynthesis and subsequent mass loss, is one of the primary ways that galaxies become enriched with heavy elements over cosmic time. The interaction between stellar winds and the surrounding interstellar medium creates some of the most beautiful structures in the galaxy. As the fast-moving wind from a hypergiant collides with the slower-moving gas and dust in space, it creates shock waves that heat up the material and make it glow. These wind-blown bubbles can extend for dozens of light years around the star, creating vast cavities in the interstellar medium. Some hypergiants are surrounded by multiple shells and structures, evidence of different episodes of mass loss throughout their lives. These nested shells tell the story of the star's evolution, like tree rings made of glowing gas extending across interstellar distances. The study of stellar winds has also revealed important details about the internal structure and evolution of massive stars. By analyzing the composition and velocity of wind material, astronomers can learn about the nuclear reactions happening deep inside the star, the temperature and density structure of the stellar atmosphere, and the magnetic fields that help channel and accelerate the wind. In some cases, stellar winds from hypergiants can actually affect star formation in their local neighborhoods. The intense radiation and fast-moving particles can heat up nearby gas clouds, preventing them from collapsing to form new stars. This creates feedback mechanisms that regulate how quickly stars form in different regions of the galaxy. There's something almost poetic about the fact that the largest stars in the universe are also the most generous, constantly giving of themselves to enrich the space around them. They shine not just with light, but with a steady stream of processed material that will eventually become part of future generations of stars and planets. These stellar winds remind us that even the most massive objects in the universe are not permanent or static. They exist in a constant state of change, gradually transforming themselves and their surroundings through the simple but profound process of atomic particles streaming away into the cosmic dark. Finding the largest stars in the universe is a bit like trying to measure the size of distant mountains while blindfolded and standing in a different country. The challenge begins with the simple fact that even the largest stars appear as mere points of light in our most powerful telescopes. Stevenson 2-18, despite being large enough to engulf Saturn's orbit, is so far away that it looks like a single pixel in our best images. Measuring the size of such an object requires not just advanced technology, but clever thinking about how to extract information from the faintest whispers of starlight. The story of discovering stellar giants is also a story of technological progress. In the early days of astronomy, when observers relied on their eyes and simple telescopes, the largest known stars were simply the brightest ones visible in the night sky. Stars like Betelgeuse and Arcturus were known to be unusually large, but determining their actual sizes was nearly impossible. The breakthrough came with the development of spectroscopy, the technique of splitting starlight into its component colors to analyze the star's composition, temperature, and other properties. By studying the spectrum of light from a star, astronomers could determine its surface temperature. Combined with measurements of the star's total brightness, this allowed them to calculate its size using relatively simple physics. Here's how this works. If you know how hot something is and how much total energy it's radiating, you can calculate its surface area and from that, its size. It's like being able to determine the size of a campfire from across a valley by measuring how warm you feel and knowing how hot the flames are. The hotter the fire, the smaller it needs to be to produce the same amount of heat at your location. But there's a complication. To measure a star's total brightness accurately, you need to know how far away it is. This is where the real detective work begins. Astronomers use a variety of techniques to measure stellar distances, from parallax measurements that track a star's apparent motion as Earth orbits the Sun, to comparisons with other stars of known properties. The development of infrared astronomy revolutionized our ability to study the largest stars. Many red hypergiants emit most of their energy in infrared wavelengths, invisible to our eyes but detectable with specialized instruments. Space-based infrared telescopes, like the Hubble Space Telescope and the Spitzer Space Telescope, opened up new windows into the world of stellar giants. Infrared observations revealed that many of the largest stars are surrounded by thick shells of dust created by their own stellar winds. This dust absorbs the star's visible light and re-radiates it in the infrared, making the star appear dimmer in visible light than it actually is. By observing in multiple wavelengths, astronomers can peer through this dust and get a clearer picture of the star itself. Another crucial technique is interferometry, where astronomers combine light from multiple telescopes to create the equivalent of a much larger telescope. This allows them to measure the angular size of the largest stars directly, seeing them as tiny disks rather than point sources. When combined with distance measurements, this gives direct measurements of stellar radii. The Hubble Space Telescope has been particularly valuable for studying stellar giants. Its high resolution and ability to observe in ultraviolet and infrared wavelengths have revealed details about stellar winds, circumstellar shells, and the complex environments around massive stars. Some of the most spectacular images of stellar nebulae and wind-blown structures come from Hubble observations. Ground-based telescopes have also made major contributions. Large telescopes like the Very Large Telescope in Chile and the Keck telescopes in Hawaii can collect enormous amounts of light, allowing astronomers to study faint details in the spectra of distant giants. Adaptive optics systems that correct for atmospheric turbulence have dramatically improved the resolution of ground-based observations. One of the ongoing challenges in measuring stellar giants is variability. Many of these stars change in brightness over time, sometimes by substantial amounts. A star that appears to be a certain size when it's bright might seem much smaller when it dims. This means astronomers often need to observe stars over long periods to get accurate measurements. The uncertainty in stellar size measurements is often quite large, especially for the most extreme objects. When astronomers say that Stevenson 2-18 has a radius of about 2,150 solar radii, that measurement might have an uncertainty of several hundred solar radii. For the largest stars, we're often dealing with rough estimates rather than precise measurements. Part of this uncertainty comes from the stars themselves. The largest hypergiants don't have well-defined surfaces like planets do. Instead, they have extended, tenuous atmospheres that gradually fade into the surrounding space. Deciding where the star ends and space begins is somewhat arbitrary, like trying to define the exact edge of a cloud. Modern surveys are discovering new stellar giants at an unprecedented rate. Projects like the 2-micron All-Sky Survey and the Gaia mission are cataloging millions of stars with unprecedented precision, revealing new candidates for the largest stars in the galaxy. Each new discovery helps refine our understanding of how massive stars evolve and what limits exist on stellar size. The search for stellar giants also benefits from citizen science projects, where amateur astronomers and volunteers help analyze astronomical data. These projects have led to the discovery of unusual variable stars and have helped identify new candidates for detailed professional study. As technology continues to advance, our ability to study stellar giants will only improve. The James Webb Space Telescope, with its unprecedented infrared capabilities, promises to reveal new details about the largest stars and their environments. Future extremely large telescopes on the ground will have the resolution to study stellar surfaces directly. This ongoing technological progress means that our current record holders for largest stars may not hold their titles forever. Each new generation of instruments reveals stars that were previously too faint or too obscured to study in detail, and some of these may turn out to be even larger than our current champions. When you're the largest star in your cosmic neighborhood, everyone feels your presence. The influence of stellar giants extends far beyond their already enormous physical boundaries, creating some of the most dynamic and spectacular environments in the galaxy. These stars don't exist in isolation. They're cosmic landscapers, constantly reshaping the space around them through their intense radiation, powerful stellar winds, and dramatic evolutionary changes. Imagine living next to a neighbor whose house is so bright you need sunglasses just to look in their direction, whose lawn sprinkler system shoots water at the speed of a hurricane, and who occasionally throws parties so loud they can be heard from several states away. That's somewhat like what it's like to be a smaller star or planet in the vicinity of a hypergiant. The most immediate effect of stellar giants is their intense luminosity. A red hypergiant like Stevenson 2-18 shines with the power of nearly 500,000 suns, flooding the surrounding space with energy across the entire electromagnetic spectrum. This radiation can heat up gas clouds dozens of light years away, causing them to glow like neon signs scattered through space. Any planets orbiting within several hundred astronomical units of such a star would be rendered uninhabitable by the intense heat. Even planets at the distance of Pluto from our Sun would be baked to temperatures hot enough to melt lead. The habitable zone around a hypergiant, where liquid water could exist on a planet's surface, would be pushed out to distances of hundreds or thousands of astronomical units. But the influence of stellar giants goes far beyond simple heating. Their intense ultraviolet radiation can ionize hydrogen gas across vast volumes of space, creating what astronomers call HII regions, glowing bubbles of plasma that can span hundreds of light years. These regions are among the most spectacular objects in the galaxy, visible as bright nebulae even in distant galaxies. The stellar winds from hypergiants create even more dramatic effects. As these high-speed particle streams collide with the surrounding interstellar medium, they create shock waves that heat the gas to millions of degrees. This creates hot bubbles of X-ray emitting plasma that can be detected by space-based X-ray telescopes. These wind-blown bubbles can grow to enormous sizes. Some hypergiants are surrounded by cavities in the interstellar medium that extend for dozens of light years in all directions. Inside these bubbles, the density of gas and dust is much lower than in normal space, creating almost empty voids heated to extreme temperatures by the stellar wind. The edges of these bubbles are often sites of active star formation. As the expanding shock wave from the stellar wind compresses gas clouds at the bubble's edge, it can trigger the collapse of these clouds and the birth of new stars. This creates a feedback loop where massive stars promote the formation of new generations of stars in their vicinity. Some of the most beautiful structures in the galaxy are created by the interaction between stellar giants and their environments. The Rosette Nebula, for example, is carved out by the combined stellar winds of several massive stars at its center. The Eagle Nebula's famous pillars of creation are sculpted by the radiation and winds from nearby massive stars, which are simultaneously destroying and revealing the dense gas columns. When hypergiants go through episodes of dramatic mass loss, they can create complex nested shell structures around themselves. These shells expand outward at different speeds, sometimes colliding with each other or with previously ejected material, creating intricate patterns of glowing gas that can persist for thousands of years. The chemical impact of stellar giants on their surroundings is equally important. As these stars lose mass through stellar winds, they're constantly enriching the surrounding space with heavy elements created through nuclear fusion in their cores. Carbon, oxygen, nitrogen, silicon, and iron produced inside the star are carried away by stellar winds and distributed throughout the local interstellar medium. This chemical enrichment affects future generations of star formation in the region. When nearby gas clouds eventually collapse to form new stars, they'll be enriched with heavy elements from the stellar winds of their massive neighbors. This can affect the properties of the new stars and any planetary systems that form around them. The gravitational influence of stellar giants can also be significant, especially in dense stellar environments like globular clusters or the cores of galaxies. A single hypergiant can gravitationally perturb the orbits of nearby stars, sometimes ejecting smaller stars from the cluster entirely or causing binary stars to merge. In binary systems where a hypergiant has a smaller companion star, the interactions can be even more dramatic. The massive star's stellar wind can strip material from its companion, while tidal forces can distort both stars' shapes. In some cases, the two stars can actually merge, creating an even more massive and unstable object. The magnetic fields of stellar giants can extend their influence even further into space. These magnetic fields can trap and accelerate charged particles from the stellar wind, creating complex magnetospheres that can affect the space environment across large volumes. When stellar giants finally reach the end of their lives, their influence on their surroundings becomes even more dramatic. The supernovae that mark the death of the most massive hypergiants can inject enormous amounts of energy into the surrounding space, creating shock waves that travel for thousands of light years and can trigger star formation across entire spiral arms of galaxies. The remnants left behind by exploding hypergiants, whether neutron stars or black holes, continue to influence their environments for millions of years after the original star is gone. Neutron stars can emit powerful beams of radiation that sweep across space like cosmic lighthouses, while black holes can accrete material from their surroundings and emit jets of particles at nearly the speed of light. Understanding these environmental effects is crucial for astronomers studying galaxy evolution and star formation. Stellar giants act as cosmic engines, driving many of the processes that shape the structure and chemical composition of galaxies over cosmic time. In a very real sense, stellar giants are among the most influential objects in the universe, shaping not just their immediate neighborhoods, but contributing to the large-scale evolution of galaxies and the cosmos as a whole. What lies ahead for the largest stars in the universe is a story written in the fundamental laws of physics, gravity, and time. The future of stellar giants is both predictable and dramatic, governed by the same nuclear processes that created them, but leading inexorably towards some of the most violent events in the cosmos. Unlike smaller stars that can live for trillions of years, these massive objects are racing towards spectacular endings that will reshape their cosmic neighborhoods and contribute to the ongoing evolution of the galaxy. For current hypergiants like Stevenson 2-18, the immediate future involves continued mass loss and instability. These stars exist in a delicate balance between gravity trying to hold them together and radiation pressure trying to blow them apart. Over the next few 100,000 years, they will continue to lose mass through powerful stellar winds, gradually shedding their outer layers into space. As these giants lose mass, they may actually become smaller and hotter, transitioning from red hypergiants to blue or yellow hypergiants before moving on to other phases of stellar evolution. This process isn't smooth or predictable, These stars can undergo sudden, dramatic changes in brightness and size as their internal structure reorganizes itself in response to changing conditions. Some hypergiants may experience what astronomers call luminous blue variable eruptions, where the star suddenly becomes much brighter and ejects large amounts of material in a single, violent event. These eruptions can be so powerful that they briefly make the star visible from other galaxies, but they're just previews of the even more dramatic events to come. The ultimate fate of the most massive hypergiants is determined by what happens in their cores. As these stars burn through successive layers of nuclear fuel, they build up increasingly heavy elements in their centers. First, helium burning creates carbon and oxygen. Then, carbon burning produces neon and magnesium. Oxygen burning creates silicon and sulfur. Finally, silicon burning produces iron and nickel. But iron represents a dead end for nuclear fusion. Unlike lighter elements, fusing iron actually absorbs energy rather than releasing it. When a massive star's core becomes predominantly iron, fusion can no longer support the star against its own gravity. What happens next depends on the exact mass of the core. For cores between about 1.5 and 3 solar masses, the collapse triggers a core collapse supernova, one of the most energetic events in the universe. In just a few seconds, the core collapses from the size of Earth to a diameter of about 20 kilometers, rebounding in an explosion that can briefly outshine an entire galaxy. The shock wave from this explosion tears through the star's outer layers, ejecting them into space at speeds of thousands of kilometers per second. But for the most massive hypergiants, with core masses above about 3 solar masses, even more extreme events are possible. These stars may undergo pair instability supernovas, explosions so powerful that they completely destroy the star, leaving behind no remnant object. In these events, the entire star is converted into energy and expelled material, creating explosions visible from billions of light years away. Some of the most massive hypergiants might skip the explosion phase entirely, collapsing directly into black holes without any visible supernova. These failed supernovas would cause the star to simply disappear from view as its light becomes trapped within the black hole's event horizon. The timing of these dramatic endings is relatively predictable for individual stars. Hypergiants like Stevenson 2-18 will likely meet their fate within the next few million years, an incredibly short time by astronomical standards. Some of the most unstable hypergiants could explode tomorrow, astronomically speaking, or they could continue burning for another million years. When these explosions occur, they will have profound effects on their surrounding environments. The shock waves will compress nearby gas clouds, potentially triggering new rounds of star formation. The heavy elements created inside the star and dispersed by the explosion will enrich the interstellar medium, providing the raw materials for future generations of stars and planets. The black holes or neutron stars left behind by these explosions will continue to influence their environments for millions of years. Black holes can accrete material from their surroundings, powering jets and outflows that can affect star formation across large regions of space. Neutron stars can emit powerful pulses of radiation as they rotate, creating cosmic lighthouses visible from thousands of light years away. Looking even further into the future, the formation of new hypergiants will depend on the availability of massive star-forming regions and the chemical composition of the galaxy. As the galaxy evolves and becomes more enriched with heavy elements, the properties of newly formed massive stars may change. In the very distant future, as the universe continues to expand and cool, star formation will gradually decline as gas becomes more dispersed and harder to collect into dense, star-forming regions. Eventually, the era of massive star formation may come to an end, and hypergiants like those we see today may become increasingly rare. But for now, we exist in a cosmic epoch where massive stars continue to form, evolve, and explode, contributing to the ongoing chemical and structural evolution of galaxies. The hypergiants we observe today are both relics of past star formation and harbingers of future cosmic events. The study of these stellar giants and their evolution also provides insights into the early universe, when the first massive stars formed from primordial hydrogen and helium. These population 3 stars may have been even more massive than today's hypergiants, living brief, brilliant lives before exploding and seeding the universe with its first heavy elements. Understanding the future of stellar giants helps astronomers model the evolution of galaxies and predict how star formation and chemical enrichment will proceed over cosmic time. These massive stars are not just spectacular objects in their own right. They are crucial actors in the ongoing story of cosmic evolution. In contemplating the future of these stellar giants, we're reminded of the dynamic, ever-changing nature of the universe. Nothing, not even the largest stars, is permanent. Everything is part of an ongoing cycle of birth, evolution, death, and renewal that has been playing out for billions of years and will continue for billions more. Sometimes the universe thinks bigger than even the largest individual stars. While we've spent our journey marveling at single stars that can grow to contain the orbit of Saturn, there are structures in the cosmos that make even these hypergiants seem modest by comparison. The universe has ways of creating objects and organizing matter on scales that stretch our understanding of what constitutes a single entity. Consider stellar associations and open clusters, where dozens or hundreds of massive stars are born together in the same stellar nursery. These groups can contain multiple hypergiants and blue supergiants, all shining together in a relatively small region of space. The combined luminosity of such a cluster can be millions of times greater than our Sun, creating some of the brightest objects visible in distant galaxies. The Cygnus OB2 association, located about 4,700 light-years from Earth, contains more than 60 O-type stars, the most massive and luminous stars on the main sequence. If you could see this association with your naked eye, it would appear as one of the brightest objects in the night sky. The combined stellar winds from these massive stars have carved out a cavity in the interstellar medium spanning more than 400 light-years across. Even more spectacular are globular clusters, ancient gravitationally bound collections of hundreds of thousands or even millions of stars packed into spherical regions just a few dozen light-years across. While most globular clusters contain primarily old, low-mass stars, in their youth they would have hosted numerous massive stars and hypergiants. The gravitational interactions within these dense environments can lead to stellar collisions and mergers, potentially creating stars even more massive than those that form in isolation. But perhaps the most extreme stellar objects are not individual stars at all, but stellar systems where multiple massive stars orbit so closely that they interact and exchange material. In these systems, stars can grow far beyond the normal mass limits by accreting material from their companions. Wolf-Rayet stars represent one extreme outcome of stellar evolution and interaction. These objects have lost their outer hydrogen layers entirely, exposing their hot, dense cores directly to space. They shine with surface temperatures of 50,000 to 100,000 degrees Celsius and emit powerful stellar winds that can exceed the mass loss rates of even the largest hypergiants. Some Wolf-Rayet stars may have started as normal massive stars but became even more extreme through interactions with binary companions. The resulting objects can be more luminous than the largest hypergiants while being much smaller and denser. They represent a different pathway to extreme stellar properties, achieved through stripping away material rather than accumulating it. Luminous blue variables, or LBVs, represent another category of extreme stellar objects. These stars undergo dramatic eruptions that can temporarily increase their brightness by factors of millions. During these eruptions, they can eject entire solar masses of material in single events, creating spectacular shells and nebulae around themselves. Eta Carinae, one of the most famous LBVs, underwent a great eruption in the 1840s that made it temporarily the second brightest star in the night sky. The eruption created the distinctive homunculus nebula, a peanut-shaped shell of ejected material that continues to expand away from the star today. At its peak, Eta Carinae may have briefly shone with the power of 5 million suns. Even more exotic are magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. While these objects are only about 20 kilometers in diameter, much smaller than any of the hypergiants we've discussed, their extreme physics creates effects that can be detected across the galaxy. A magnetar's magnetic field is so strong that it warps the quantum vacuum around the star, and powerful magnetic reconnection events can release more energy in a few seconds than our Sun emits in years. On the largest scales, entire galaxies can be thought of as single, coherent objects. The Milky Way galaxy contains roughly 400 billion stars and has a diameter of about 100,000 light-years. If our galaxy were shrunk down so that our Sun was the size of a grain of sand, the entire galaxy would still be larger than the continental United States. Some galaxies are much larger than the Milky Way. IC 1101, one of the largest known galaxies, has a diameter of about 6 million light-years and contains an estimated 100 trillion stars. Such galaxies are cosmic giants in their own right, containing more mass than millions of galaxies like our own. Galaxy clusters represent an even larger scale of cosmic organization. The Coma cluster contains over 1,000 known galaxies within a region about 20 million light-years across. The total mass of such a cluster, including dark matter, can be equivalent to hundreds of trillions of stars. But perhaps the most mind-bending cosmic structures are the largest known objects in the universe: galaxy superclusters and cosmic filaments. The Hercules Corona Borealis Great Wall is a structure of galaxy clusters and superclusters that spans about 10 billion light-years across, roughly 10% of the diameter of the observable universe. These largest cosmic structures remind us that scale in the universe extends far beyond individual objects, no matter how large. While stellar hypergiants represent the upper limits of what single stars can achieve, they are embedded within increasingly larger structures that organize matter on scales approaching the cosmic horizon itself. Yet there's something beautiful about the connection between these vastly different scales. The heavy elements created inside hypergiants and distributed by their stellar winds and explosive deaths become the building blocks for planets, life, and eventually conscious beings capable of contemplating the cosmic hierarchy of which they are part. In studying the largest stars, we're not just learning about extreme stellar physics, but about our place in a universe that contains structures ranging from subatomic particles to cosmic filaments, billions of light-years across. Each scale of organization, from the quantum to the cosmic, plays a role in creating the conditions that make stars, planets, and life possible. The universe is a hierarchy of nested structures, and stellar hypergiants occupy a special place in this hierarchy as the largest individual objects capable of nuclear fusion, the largest single entities that can truly be called stars. They represent the ultimate expression of stellar gigantism while remaining part of the larger cosmic web that connects everything in the universe. And so, we arrive at the end of our gentle voyage through the realm of stellar giants, where we've met objects so large they stretch the boundaries of imagination itself. We began with Earth, our familiar marble of a world, and journeyed outward through failed stars and stellar wannabes, past the dependable red dwarfs and sun-like stars, beyond the brilliant blue giants burning bright and fast, until we reached the true monsters, hypergiants so large that our sun would be lost like a grain of sand on their vast glowing surfaces. Along the way, we've discovered that size in the universe is both more extreme and more nuanced than we might have expected. The largest stars aren't necessarily the most massive ones. The brightest aren't always the longest lived, and sometimes, to become truly gigantic, a star must first begin to die, swelling up in its final phases like a cosmic balloon made of fire and light. We've learned that Stevenson 2-18, our current record holder, is so large that light takes 9 hours to travel around it. We've seen that even the most massive stars are limited by their own brilliance, blowing themselves apart with the intensity of their nuclear fires. And we've discovered that all these stellar giants are part of an endless cycle of birth, death, and renewal that has been shaping the galaxy for billions of years. We've explored how astronomers measure objects so distant they appear as single points of light, how stellar winds carry away entire solar masses of material, and how these cosmic giants reshape entire neighborhoods of space with their powerful radiation and explosive deaths. We've glimpsed their dramatic futures and seen how they connect to even larger structures that span the observable universe. Tonight, as you settle into sleep, perhaps you'll carry with you a sense of the cosmic scale that surrounds us. Every atom in your body was once inside a star, processed by nuclear fusion in stellar cores, scattered by stellar winds and supernova explosions, and eventually gathered up to become part of you. You are connected to these distant giants in the most fundamental way possible. The title of our journey tonight included those important words, "for now." The largest star we know today may not hold that title forever. As our instruments improve and we explore more of the galaxy, we may find even larger objects, red hypergiants that make our current record holders seem small by comparison. But perhaps that's part of the wonder. The universe continues to surprise us, to exceed our expectations, to reveal new scales of grandeur that humble and inspire us in equal measure. In a cosmos filled with objects larger than we can truly comprehend, there's something comforting about knowing that the story isn't finished yet. If you found any peace in this cosmic journey, if the gentle giants of space helped calm your thoughts, or if the questions sparked gentle dreams about the nature of size and scale, we'd be honored if you follow us for more wandering explorations through the mysteries of science. Thanks for joining us here at Sleep Science. Sleep well and dream of stars.